Limited, Pune, and retired as General Manager R&D. He is the visiting professor for graduate engineering at Department of Technology, Pune University. He is currently working as RAC consultant specialization in operation theatre and industrial air conditioning. He is the chairman of ISHRAE Committee for the Heat Load and Moisture Impact and Control HVAC Data Book Updation projects. So these are all about our speaker for today's session. And the topic is again a very interesting one, which is misconceptions in psychrometrics. So I welcome each and every one of you for participating in this webinar, which is organized by ISHRAE under the banner of Technical Committee. So we would be definitely hearing for the insightful information that will be shared by the speaker. So thank you very much and looking forward to the speaker's presentation. Over to you, Mukund sir, please.
Thank you, Moni. And thank you everyone or ISHRAE for giving me the opportunity to share my thoughts here. So I will just start my presentation right away. The entire presentation is based on two books. One is Understanding Psychrometrics. It is an ISHRAE book. And the second is ISHRAE Handbook, of course, Fundamental. So that is the second book which is being used for giving this presentation. So let us start. There are about 9 misconceptions. And the 10th one I have given as a puzzle, which I expect the last slide has my email ID. So I don't expect any answer during this webinar. So whosoever feels that he can solve the puzzle, he can write to me with the answer, because otherwise if we start speaking for the answer, there could be confusion. So let us start. The first myth or misconception is about absolute humidity. Many people take that the y-axis of psychrometric chart, as you see here, is considered as a absolute humidity. So that is a misconception. It is not absolute humidity. So how it is? So what are the units of psychrometric chart on the y-axis? It is kg of moisture per kg of dry air or grains per pound of dry air. What is the unit of absolute humidity by ISHRAE? ISHRAE defines absolute humidity as the ratio of mass of water vapor to the total volume of the sample. So it is related to the volume of the sample. So absolute humidity is not kg of moisture per kg of dry air, but it is kg of moisture per volume of the sample. Sometimes people take as a specific humidity, but just specific, okay, that I will. So the unit of absolute humidity is kg per cubic meter and not kg per kg. So humidity ratio is defined by ISHRAE as the ratio of mass of water vapor to mass of dry air in the sample, which is what is given as a y-axis in the psychrometric chart. As I said, there is one more humidity called specific humidity, which is the ratio of mass of water vapor to the total mass of moist air, while humidity ratio is mass of moisture divided by mass of dry air, which is the y-axis of psychrometric chart. Specific humidity is the ratio, denominator is the total mass of moist air. And as I told you, absolute humidity, denominator is the total volume. So first simple misconception that y-axis of psychrometric chart does not denote absolute humidity, but humidity ratio. Second is relative humidity. Many people, I found that they take the definition of relative humidity is mass of water vapor present per kg of dry air at certain pressure and temperature. 2. Mass of water vapor per kg of dry air when the air is saturated with water vapor at the same temperature and the pressure. This is what many people take as a definition of relative humidity, which is not correct. Actually, this particular ratio is called as degree of saturation. So ISHRAE defines degree of saturation as the ratio of humidity ratio W to humidity ratio Ws of saturated moist air at the same temperature and the pressure. There is a relation between degree of saturation and relative humidity, which we will see in the next slide. Understanding psychrometrics says under the degree of saturation, where I have made this circle, many people and some texts incorrectly use this definition as a degree of saturation for relative humidity, which is what I also found that many people are assuming that that is the definition of relative humidity, which is wrong. सलोनी, एक बार आप सुनाई बराबर दे रहा है करके, can you just tell me? Or Mr. Moni?
Yes, sir. Yes, sir.
Okay, thank you. So what is the ISHRAE fundamental definition of relative humidity? Relative humidity as defined by ISHRAE is the ratio of PW upon PWS. What is PW? Is the partial pressure of water vapor, which is within the air, divided by partial pressure of water vapor if the same air becomes saturated at the same pressure and temperature. Now, many people feel that this does not give any exact idea what about that. So we will see how we can get more significance or more practical idea. But as I said, that there are two definitions. One is relative humidity and one is degree of saturation. And many people degree of saturation is taking as relative humidity. So there is an equation given by ISHRAE that how relative humidity phi is mathematically related to mu, which is degree of saturation. Now, at 0% RH and 100% RH, both mu and phi, which is relative humidity, are equal. But at 50% RH and particularly at higher temperature, the difference is very large. For example, as you can see in the right side, at 40 degrees centigrade, if we take RH as 50%, then W upon Ws mu is only 48.1%, and the difference is almost 2%. The book Understanding Psychrometrics goes further and says that, for example, Webster's dictionary is saying that the relative humidity is the ratio of amount of water vapor present in the air to the greatest possible amount of moisture in the same temperature. This is not correct, but the Understanding Psychrometric book says if the word same volume are added at the end, then the definition would be complete and scientific. Now, as I said, if I take a definition of ratio of partial pressure, we don't get feeling of this thing. But the moment the definition which is come in the next slide is coming based on this understanding psychrometric addition of volume, then we get good feeling that what is the relative humidity. So the relative humidity in that case, as defined by the understanding psychrometric, for people to understand, is relative humidity is the ratio of actual mass of water vapor in a given volume of moist air to the mass of water vapor in the same volume of saturated air at same temperature and pressure. So in both the cases, if we assume that the volume, pressure and temperature is same, then ratio of mass of water vapor present divided by mass of water vapor maximum can become a relative humidity. How it can become a relative humidity and how it matches with the ISHRAE definition, will come now. क्या होगा? एक मिनट, नहीं आ रहा है. Next slide. For unsaturated water vapor, that means the air which is currently present is unsaturated. So we can just write an equation for only water vapor. PW into VW is equal to MWR into T, which is PV is equal to MRT, famous equation of the gas laws, where PW is a partial pressure of water vapor in the unsaturated condition. VW is the volume, MW is the mass of water vapor present, R is the gas constant for water vapor, and T is the temperature. Now, if we saturate the air without change in temperature and volume, and also the total pressure remaining same, then the partial pressure will be now PWS into VWS is equal to MWS. MWS stands for maximum amount of water which can under saturated condition for the same temperature and pressure and volume. The equation will be PWS upon VWS is equal to MWS upon R into T, where S represents saturated vapor. Now, by definition, which is given above, we are saying even volume is also constant. So, if I take a ratio of left-hand side of both the equation, that is PW upon VW divided by PWS upon VWS, by definition, both V are same. So, PW upon PWS will become equal to MW upon MWS because R and T are constant. So, if I use this definition, then the ratio of mass of water vapor present in the air divided by mass of water vapor present, maximum amount of mass of water vapor that can be present under same temperature, total pressure and volume, then it will become PW by PWS, which is the ISHRAE definition. That means the relative humidity definition, it is the ratio of actual mass of water vapor in a given volume of moist air. If we use, then we are coming to the same definition of ISHRAE, which is ratio of partial pressure. Only thing is, by ratio of partial pressure, we don't get a feeling, but by putting a volume, we get a good feeling, and it is technically also correct. Let us go the third myth, which is dew point temperature. The dew point temperature many people take, that is the temperature at which condensation of moisture just begins. That means we are cooling the air, and when the first drop comes out, that is the temperature many people call as a dew point temperature. But what does ISHRAE terminology say? They say that it is improper to refer to the dew point as the temperature at which condensation starts to occur, because the condensation at dew point requires removal of latent heat from the vapor to induce condensation, and this can occur only if the vapor is cooled below the dew point. That means the first drop will occur only if we go below the dew point, then only the first drop will occur. So, what is the correct definition? This understanding psychrometric defines the dew point for two ways. One, he says lay person's definition. We are engineers, we are not lay persons. So the lay person's definition is the same what many people take, the surface temperature at which dew or frost first forms, or the surface temperature at which water vapor just starts to condense. But the engineer's definition or ISHRAE definition is the dew point temperature is the temperature of moist air saturated at pressure P. That means the air is saturated, but the first drop has not come out. That temperature is the correct dew point temperature as defined by ISHRAE fundamentals. Now let us go to fourth myth as a enthalpy. Now let us say that we have two airs. One is having higher dry bulb temperature and certain wet bulb, and the other is having lower wet bulb temperature, lower dry bulb temperature, but the same wet bulb temperature. For example, if we say that enthalpy at 50 degrees dB and 21 wet bulb, And if we compare with 21-degree dry bulb and 21-degree wet bulb, many people feel, wet bulb is same, but dry bulb is higher, 50 degree. So the enthalpy of 50 degree dB and 21 degree wet bulb should be more than 21, or at least same or slightly more than 21 degree dry bulb and 21 degree wet bulb, which is wrong. Actually, the enthalpy of air at 50 degree dry bulb and 20 degree wet bulb will be less than the enthalpy, slightly less than the enthalpy of 21 degree dry bulb and 21 degree wet bulb. First, let us see the psychrometric chart to prove this point, and then let us understand why it happens. So this is a psychrometric chart. Now, as you see my cursor, the red line is an enthalpy line and the blue line is the wet bulb line. Okay. So if I have 50 degree, now if you see the enthalpy line is making small angle with respect to wet bulb line. As you see here, the distance between the wet bulb line and the enthalpy line, which is the red color, is maximum at saturation point, and they are coinciding at highest temperature. So if I want to know the enthalpy of 50 degree dry bulb and 21 degree wet bulb, then I go along the red line and see the enthalpy here, which is 62 kilojoule per kg. But if I want to see the enthalpy of 21 degree dry bulb and 21 degree wet bulb, then I go here along with the wet bulb line of 21 degree and measure the enthalpy here, which is 62.1 kilojoule per kg, which means the enthalpy of air at 21 degree dry bulb and 21 wet bulb is 62.1, while the enthalpy of air at 50 degree dry bulb and 21 degree wet bulb is slightly by 0.1 kilojoule less as compared to this. So this is very clear from psychrometric chart, but let us understand the reason behind this. So you know that the wet bulb temperature, thermodynamic wet bulb temperature is, if I take some air, which is unsaturated air, and pass through a infinity long tunnel, which is completely insulated, and the water is spread over there, the length is so high that at the end the air is completely saturated, so the dry bulb and wet bulb is same, then we call that this is the wet bulb temperature of the air which is entering in the duct, infinite length duct. So if I have 50 degree dry bulb and 21 degree wet bulb, since there is no heat is coming in or going out because it is a completely insulated vessel, so what is addition? The addition only small amount of water. So if I want to find out the equation of enthalpy, and if I take the enthalpy of inlet air as H1, then how I do find the enthalpy at outlet? I know I have added some water, which is the water at the outlet is WS star and water at the inlet is W1. So I have added the water WS star minus W1 into the enthalpy of water. So if I want to find the enthalpy on the right hand side, which is 21 degree dry bulb and 21 degree wet bulb, I have to find it by H1 plus something is equal to H star, which is the enthalpy of the completely saturated air. So the right hand side 21 degree dry bulb and 21 degree wet bulb enthalpy is inlet enthalpy H1 plus something. Naturally, the outlet enthalpy is higher than the inlet enthalpy, and that is how 50 degree dry bulb and 21 degree wet bulb enthalpy is slightly less than 21 degree dry bulb and 21 degree wet bulb. By natural logic, people feel temperature is high, wet bulb is same, so the enthalpy should be slightly more, which is exactly opposite. Now let us go to next myth, air density. Now, if we have two air at the same temperature and pressure, and one is having higher moisture and content, and the other is having lower moisture content, then similarly, like last time, people may feel temperature is same, total pressure is same and the moisture is higher in the first air, so the density will be higher. That is what many people consider. But it is exactly opposite. Let us see again in psychrometric chart whether what is true. So let us take air A is at 34 degrees centigrade with moisture at 4 grams per kg of dry air, and air B is at 34 degrees centigrade, and that is the temperature remains same, but the moisture is as high as 21.7 gram per kg of dry air. So the misconception people have, temperature is same, total pressure is same, since it has got more moisture, the air A will be lighter and air B will be, which is having higher moisture, will be higher or dense or having more weight, which is wrong. So let us first see in the psychrometric chart what is the fact. So we are going to see at 34 degrees centigrade and 4 gram the density of which is given in the psychrometric chart, and also at 34 degree and 21.7 gram what is the density given in the psychrometric chart. Now in the psychrometric chart normally specific volume is given. Specific volume is 1 upon density. So if specific volume is more, density is low. So let us draw a point 34 degree and 4 grams of moisture. So this is the point which the specific volume is 0.875. And if I have the same temperature and go to 21.7 moisture content, then you will see the specific volume is 0.9. So 0.875 specific volume for lower moisture has turned to 0.9. If I find in the density terms, which we have more feeling, the lower moisture has a density of 1.14, while the higher moisture has a density of 1.11. So that means the air which is having less moisture has got higher density as compared to the air which has got higher moisture, even though the temperature and total pressure is same. So we definitely now know that the moisture content increases, density decreases. But let us understand why this happens. Now, density of air is dominated by the density of dry air. The density of moist air is dominated by density of dry air because the water vapor is present at a partial pressure very, very low. So naturally the density of water vapor is extremely low because the partial pressure is very, very low. It's in high vacuum. So it is dominated by the dry air density. The moment moisture increases, the partial pressure of dry air reduces. And if the partial pressure of dry air reduces, the density of dry air by simple gas law will reduce. And since it is the dominating factor for total density, the actual density will go on reducing if the total pressure remains same, total pressure and temperature remain same, and the dry air component reduces, because the moment the partial pressure of dry air will reduce and the density will reduce. So that is the another misconception people have, that the more the moisture, more the density, but which is exactly opposite. Now the next myth is psychrometric chart. Now everybody has seen the psychrometric chart, so people feel there is only one psychrometric chart. But for air, there are more than one psychrometric chart. But for air conditioning engineer, we use, there are two types of psychrometric chart and not one type of psychrometric chart. So let us understand. There are two basic coordinates. One is enthalpy and moisture chart, which is called as HW chart, where the psychrometric chart is plotted using the enthalpy scale and the humidity scale, and the dry bulb temperature is the derived function. So when it is plotting, first the enthalpy axis is drawn, then the moisture content axis is drawn, and then the entire like relative humidity, dry bulb, specific. So that is one type of chart which is used by ISHRAE. But there is another chart which we feel that it is the actual coordinates, which is TW chart, where the dry bulb temperature is the axis and the moisture content is the axis. So usually most of the manufacturers like Train, Carrier, York, they use a TW chart, but ISHRAE or CIBSC, which is taken as a base for air conditioning industry, they are using HW chart. Let us see the example. If we see the ISHRAE psychrometric chart, and if we go for the 0 degrees centigrade, actually the dry bulb lines are slightly slant. So if we go to the entire left, you can know that the dry bulb lines are not vertical. Why they are not vertical? Because it's a derived axis. This particular chart has been drawn by first drawing the enthalpy and the moisture content, and the dry bulb as well as RH all are derived function, and in the derived function this is not a straight line, which will be, angle being small, we don't come to know immediately. But if you go to the left hand side maximum, then we come to know, array, this is a slant line and this is not a straight line. But if you give, for example, to the Carrier psychrometric chart, then you will see at the end, even if -10, the line is perfectly vertical. Why? Because this chart has been drawn taking dry bulb temperature as an axis and moisture content as an axis. And that is why this particular line, which is dry bulb line, in these are perfectly vertical, unlike the ISHRAE chart. Now the next myth is cooling coil outlet air is a mixture of saturated air and bypass. That is what we normally take. So to represent graphically, suppose there is air at one point and the surface temperature of the coil, average surface temperature of the coil is 2. Then what we take, some of the air which will go follow the process of red and it will go and come to the point 2. And some air will get bypassed and the point 2 and point 1 will mix and we will get a mixture point. This is very convenient for all the calculations and procedure and methodology. But actually this is not a fact. So let us understand how it is. Actually the bypass factor is a phrase coined to get state 2 because it is very convenient. For example, if we take a simple sensible cooling and if we have a coil at a surface temperature of 3 and we have the air entering the coil is at 1, and let us assume that it's only sensible cooling. Now if the surface temperature of the coil is T3, you will require and if you want to achieve the temperature of T3 at the outlet of the air, you will require infinitely large coil, which is only theoretically possible. Unless we have infinity heat transfer area, we really can't get to T3. So every coil has got some efficiency, heat exchanger has got some efficiency. So we will land up somewhere in the point 2 when the surface temperature is 3 and the inlet is 1, outlet is 2 and surface temperature is 3 because of the inefficiency of the coil, because we are not giving infinitely large surface area. Now what happens is, if we assume that if we have an infinity large coil over here and X amount is bypassed out of one unit of air, then 1 minus X will reach at the exact surface temperature of the coil and X kg will reach at, that means 1 minus X will reach at 0.3 and X kg will reach at 0.1, and if we mix together, then again we get 0.2. So the result is the same. If we assume that if there is some air is getting bypassed, and if we assume the air is not getting bypassed, but it is inefficiency of the coil, then the result is the same. And that is why this particular bypass factor phase is coined to get state 2. Actually what happens, let us say a cooling coil is having 12 fins per inch So the distance between two fins is only 2 mm, and it is going at very high speed, very highly turbulent flow, 2.5 meter per second velocity. So not only the air molecules are continuously hitting within the fin, within the coil depth, not only the air molecules are continuously hitting the coil and the fins, but they are hitting with each other also, and transferring the heat to individual molecule from one molecule to other molecule when they collide. So actually the hardly any is actually bypass. That means untreated air as it comes, it doesn't come out. But it is very convenient factor, because mathematically it becomes very simple. So in actual practice, no air is completely bypassed, but exchanges heat within itself only, and it is a mixture that comes out. So we should get to know that though bypass factor term is used very conveniently and mathematically, actually there is no bypass of the air, which is coming at one temperature and coming out of the coil without change in temperature and RH. Next two misconceptions are difficult to put in one line, like so far first 7 misconceptions. So hence it is given in the form of question. If there is no misconception, the answer will be easy. So what is the misconception about wet bulb temperature? Now the teacher was explaining, see the figure at the bottom right. Now what is the bottom right figure? There is a cooling tower, and from the basin there is a pump which is pumping the water back to the cooling tower. There is no process heating or cooling in between. So it is just recirculating the water to the cooling tower, and we are assuming the pump HP is so small that it is not really creating any load over there. So the teacher, this condition is called as no load condition cooling tower. So teacher was teaching wet bulb temperature or cooling tower, and he says that the minimum temperature at which the cooling tower can give is the wet bulb temperature under the no load condition. That is what the teacher told the students. But one smart student said, no, sir, I don't accept it. He says, why you don't accept it? He said, the air that is coming, let us say the air is coming at 35-degree dry bulb and 28-degree wet bulb, and it has achieved 28 because long time it was moving continuously, and it has already achieved 28 degrees. So the water temperature is now 28 degrees. But 35-degree dry bulb and 28-degree dry bulb, wet bulb, is an unsaturated air. So it is hungry for moisture. So as this 28 degrees water will be sprayed over here, then some of the moisture, some of the water will go within the air which is coming at 35-degree dry bulb and 28-degree wet bulb. And that moisture, when it goes in the form of vapor form, the latent heat required for converting that liquid water to vapor water will be taken by water itself, and naturally the temperature should go down below 28 degrees Celsius, because it is still getting vaporized, because every time the air coming is a new air which is at 35-degree and 28 wet bulb, which is unsaturated air. So some moisture will definitely. Just to get more clarity, at saturation pressure of water vapor at 28 degrees is 3784 Pascal, while the partial pressure of water vapor is 3328 Pascal. So even my partial pressure is also of water vapor is lower than the saturation pressure at 28. So definitely some of the water, liquid water, will go in the vapor. So the student said, no, sir, it should go below 28 degrees under no load condition. Now, the question, as I said, this myth is explained, or this misconception is explained through the question. So the question is, what was the student missing? We all know that it cannot go lower than wet bulb, but student had given a perfect logic. So what is the mistake in logic? If we understand that, then we understand more about wet bulb temperature. So let me explain that what was the student missing. Just to continue I will just explain the wet bulb temperature a little bit elaborately. We all know that if you have a dry bulb thermometer connected to the bulb is covered with Muslim wet cloth and the water is coming by capillary action. And if we take the air at, let us say, 500 FEM or 250 FEM, 5 meter per second velocity, then there will be a drop in the mercury in this particular thermometer. And when the mercury goes down and stabilizes, that temperature we call as a wet bulb temperature. Now, why the mercury goes down? The mercury goes down because muslin cloth around the bulb of thermometer takes water by capillary action. Unsaturated moist air, when passes on the cloth, water vapor from the cloth goes to moist air by mass transfer. But going water from cloth to moist air, it must be turned to vapor from liquid water. The latent heat required by turning liquid water to vapor is taken from wet cloth, which is the same principle of earthen pot, and hence the temperature drops down, and thermometer bulb measures the temperature of the wick because the bulb is fully surrounded very closely with the wick, and it measures the temperature of the wick, and the wick temperature goes down because of the mass transfer, and that is how we measure the wet bulb thermometer temperature. Now we are going back to the students' miss point. So we all know that the rate of heat transfer depends on delta T. That means if there are two surfaces, the surface A has got, let us say, 200 degrees temperature, and surface B has got 100 degree temperature, then the Q will be directly proportional to delta T. As the delta T will increase, the Q will increase. That is how we know all the heat transfer takes place, and the K is the constant for that. This is all very clear. But for mass transfer, what happens? Let us understand. So let us have this same wet bulb thermometer. So the air is coming at partial pressure of water vapor P2, and the saturation pressure of water which is there in the wick at that instant. If we see with respect to steam table, and if we see the P1, then the mass transfer, like that heat transfer depends on delta T, the mass transfer depends on P1 minus P2. So the mass transfer is equal to K into P1 minus P2, where P1 is the saturation pressure of water present in the wick, and P2 is the partial pressure of water vapor which is there in the air. So mass transfer is equal to K into delta P. So like Q is directly proportional to delta T, mass transfer is directly proportional to delta P. So drier the air passing, you know what happens? As the air becomes more and more dry, the more amount of dry air is there, less amount of water vapor is there. So partial pressure of water vapor is lower and lower. So difference between P1 and P2 is more. So more amount of water vapor gets transferred, water gets into the water vapor, and that is why we get more depression or wet bulb depression over here, and because the mass transfer is high. So the drier the air passing on the wet bulb thermometer, more will be the moisture transfer. As the drier air will have lower partial pressure, and hence more delta P and more wet bulb depression. But now we will see very interesting fact. Here is the graph which is drawn. On the x-axis is the temperature, and on the y-axis is the pressure. Now there are two lines which are drawn. The first line is simple. The air is continuously coming, and let us assume for 15 minutes, half an hour, the air property does not change. For the time being, we'll assume that dry bulb and wet bulb is same. So every time the new air is coming to wet bulb thermometer, but the air temperature is same, air moisture content is same. So naturally, the partial pressure is also same. So this line is horizontal. Now we have just put the cloth around the bulb of the wet bulb thermometer, and just we have taken the water and it is now put in the by capillary action, the water has come into the wick. Now let us say that the water temperature and air temperature is same initially. So we have 35 degrees water, 35 degrees dry air temperature, 35 degrees water temperature, so 35 degrees wick temperature. So the mass transfer will happen based on this delta P, that is the partial pressure of water vapor in the air, unsaturated air, and the saturation pressure at 35 degrees centigrade. This will be the delta P. Now what happens? As the moisture transfer starts, the temperature of the wick starts going down. So the temperature of the wick will start going down from right to left. So let us say we come at delta P2. So where the temperature of the water has now dropped to 31 degrees centigrade, because the moisture has evaporated and the latent heat for moisture has been taken from the wick itself. So the water temperature is now no longer 35, which is 31. But the moment it becomes 31, the saturation pressure has dropped. So the potential for mass transfer, which is delta P2, has dropped. And finally, it will continuously go on dropping till the temperature of wick will start reducing. So the mass transfer, as I say, is the K into delta P, and heat transfer K into delta T. So as the wick temperature falls down, delta P starts reducing the mass transfer rate. Initially, the mass transfer rate will be very high. As the wick temperature starts reducing, the temperature starts going down, and the rate of dropping the mercury in the wet bulb thermometer will be slower and slower. Now there is a heat balance, because heat and mass balance forces are there. Because let us say the air is at 35 degrees centigrade and this has dropped at 31 degrees centigrade. So now the wick temperature is 31. So this wick will get heated sensibly by 35 degrees air. So there is now heat transfer force generated because of the delta T, which is the 35 degrees the dry bulb, and the wick temperature is only 31. Let us assume for some time being. So naturally there is a delta T. So the 35 degrees air hitting the air sensibly. So as the temperature of the wet bulb start dropping, delta T is generated, and as the wick temperature falls down, delta T increases and the rate of heat transfer increases. So as the suppose it 31 degree becomes 30 degree, the rate of heat transfer will increase because the delta T is increased and heat transfer is directly proportional to delta T. So moisture at higher temperature will start sensibly heating wick. More the drop, more is the sensible heating. Now, most interesting fact is mass transfer is trying to lower the temperature, because by mass transfer, the latent heat is taken by the wick. But as the wick temperature falls, the rate of mass transfer reduces and rate of lowering the temperature also reduces. But the moment the temperature starts going down, the heat transfer is trying to increase the temperature, and as the wick temperature falls, this rate increases because the delta T increases. So at some point, those two forces becomes exactly equal. So when the heating force and the cooling force becomes exactly equal, the mercury will get completely stabilized. It will not go up or it will go down. And then in that temperature, we will call as a wet bulb temperature. For simplicity, I have taken only convection, but there is a radiation component also. So if we are doing the equations, then we have to take into the account the some radiation component also. But for simplicity, I have just taken the convection component. Now we understand what the student was missing. The temperature had come down to 28 degrees centigrade water, and 28 degrees centigrade water has a higher 28 degrees centigrade water has higher water vapor pressure than the partial pressure of water. So definitely the water will evaporate and some of the water will go into the air and it will try to reduce the temperature of the water. But simultaneously, that 35 degrees water air will heat that 28 degrees water. And by definition, of the wet bulb temperature, when the both forces are equal, then that temperature is called wet bulb temperature. So exactly the same phenomenon takes place in the cooling tower. And that is why in the cooling tower, the temperature can never go below wet bulb, because though the evaporation will occur, the cooling force equal to heating force, and that is why the minimum temperature which we can theoretically get, if we assume there is no pump power or negligible pump power, we can only get up to the wet bulb temperature. Now, the last misconception before the puzzle is cooling and dehumidification process part. This is the example taken from ISHRAE fundamental. We are not going to the example, but if we see here the cooling and dehumidification process, the line is shown as dotted line, which is not straight. We are very used to see as a straight line. So this is a dotted line and this is not straight line. So the question is, why the process 1, 2 is not shown as a straight line normally we draw in the psychrometric processes. So if we see on the figure, cooling coil process, and this is about 8-row cooling coil. Now usually what happens, most of the time the air entering, which is in the first row of the coil, is unsaturated and higher temperature than the fluid which is inside the tube. So the more sensible load is there, till the dew point is reached, the load is 100% sensible for some time. So naturally, initially the process is more horizontal, and as you go further and further, the process takes more and more latent heat, and the horizontal, instead of horizontal component, the vertical component increases, and hence the line is always curved line from start to finish the process, and it is not a straight line what we take in the psychrometric process normally. Initially, unless the air is 100% saturated, which is very rare case, initially it will take only sensible load. So when it takes only sensible load, the line will be horizontal, and maybe in the same process it will take some of the moisture. So the line will be again going down as shown over there. But very interesting fact is there is one straight line law in the psychrometrics. Now, this is the process what we use in the air conditioning. A is the room condition, C is the outside air condition, and D is the mixed air condition. And then it passes on the cooling coil, which has got ADP as shown over here. And we say that there is a bypass factor, and we get at point F, which is the coil outlet condition. And this is the first row, second row, third row, and fourth row. This is the 4-row coil. So the actual process may be 2, 3, 1, 2, 3, 4. But the straight line law says that whatever is the process over there, the final point of the last row will always fall on the straight line joining the point 1 and the ADP. So that is what is called a straight line law. The process is D, E, F, but it is no surprise that the warm air at point D drops to the point B when in contact with the surface temperature at the ADP. What is surprising is the rate of heat transfer and mass transfer are so related, the point F always fall on the straight line joining point D and T ADP, even though the actual process join D and F need not be straight line. That means if you have 3-row coil, then this 3 point again will fall on the straight line. If you have 2-row coil, again this point will fall on the. So the last row, and there is a big derivation given in the books of how this happens or how this is proved. So this is not a law, this is a proven derivation over there. though it is called as a law, it is a derivation, it is a, there is a derivation for this. And the last point, the final point of the last row always falls. And that is why we always draw a straight line, because we are not really concerned about in-between process. We are only concerned about the final process. And the straight line drawing is also correct, but we should know that actual process is not straight line. It is coming to the point 4, joining at the point 4, but the process is slightly different. So this will complete about 9 miss points, and now it is a time of puzzle. The last point is the point of puzzle. Let us say we have a very high monsoon and we have 30 degrees centigrade temperature, and the wet bulb temperature is also about 29 wet bulb. And we are passing this air on the cooling coil, which is at 10 degrees centigrade. So if we see the process, and if we assume a bypass factor of 15%, then we will reach at this point. Now this point is a fog region. So we will come to the fog region. Many of you would have gone by aeroplane in the monsoon season when the plane is yet to take off. The doors are open, and if you are in either Calcutta or Chennai or Bombay, and the monsoon is it is raining, the outside RH is very high, you will see the fog coming out of the outlets in the aeroplane. I am sure many would have seen that. So the final point comes over here at A. Now what is the puzzle? So it is quite sure that many of you have seen that fog, because the final point lies in this region, which is the fog region. Now the puzzle is, if I want to find the dew point of this temperature, let us say if I draw here, the dry bulb temperature is something like 14.5 degrees centigrade. Now if I want a dew point, as you see on the left hand side curve, I have to go to saturation curve and come here. So in that case, the puzzle is, will the dew point be 15 degrees centigrade? That means the dry bulb temperature is only 13.5 degrees centigrade and the dew point is 15 degrees centigrade. So will the dew point temperature of point A will be higher than dry bulb? Normally the dew point temperature is lower. So the puzzle is, will the dew point temperature of this fog point will be higher than the dry bulb temperature or not? This is the last puzzle which is given. Whosoever is interested to can give the answer in the below email ID, msranade@gmail.com. I don't want to discuss this in this particular lecture or webinar, because there could be many more controversy in that. So if you write to me what is the correct answer, I will assure you that I will reply. Thank you very much for listening to me, and I will take this over to ISHRAE, Saloni or Mr. Moni. Thank you. Hello. 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 Is there anybody over there? Anybody there? Mr. Moni? Saloni? If there are any questions apart from the puzzle, I can take it. But Mr. Moni or Miss Saloni or Mrs. Saloni or Moni, please join. Saloni or Moni, please join. I will try to ring her, because she has to unmute you if anybody wants to ask the question. Hello. My lecture is over now. If people have questions, they can ask or I can leave.
Okay, sir. Okay, sir.
Yeah. So you ask people if they have any question. I don't know whether they have questions or not. Otherwise, we can finish this webinar. It was time for 1 hour and I finished almost, I think, exactly in 1 hour. क्या है?
Sir, no one.
So then formally close the program, no?
Yeah, okay, sir. I'll end the webinar if no one asks the question.
So should
So can I end?
there are 22 question answer I am seeing there.
Yes, sir. Yes, sir.
At
It's
least I can
23.
read few of them. Okay. Can you suggest a good reference book on psychrometrics? I already suggested that understanding psychrometrics by and I have in my webinar there is a photo of the cover page also. Did you say adiabatic cooling is not constant enthalpy process? Of course it is not, because we are adding moisture into it. So the enthalpy is slightly high. It is very clear from the psychrometric chart. 50 degrees, 21 degree has a some enthalpy, and 21 degree, 21 by wet bulb has different enthalpy. So it is a constant wet bulb process, but not constant enthalpy process. Is it not better to call WBT a property of water and not the air? Wet bulb temperature is a definitely property of air. Dry bulb and wet bulb temperature is a property of air. Sir, please explain how ASH is drawn on psychrometric chart and significance of it. This question does not relate to basic psychrometrics. It is a question of it is related to applied psychrometrics. So I think I have a seminar on sometime on applied psychometrics. Many times I take courses, so there I can explain. Thank you. Thank you. Can we rely on stationary hygrometer or reeling hygrometer? Reeling hygrometer has a problem that you have to stop for the taking the reading, and during that time the temperature changes. So stationary hygrometer with the fan giving the air is the best. Can you summarize all nice misconceptions? I think this Saloni, don't know go on this. Somebody has asked, can you summarize all 9 misconceptions? Is this seminar available or webinar is going to be available for everyone if there is a ISHRAE member? Because that's what I was told by Nishant.
Yes, sir. It is recording, so I can share.
Yeah. So you can, if you are a member of ISHRAE, you can contact ISHRAE head office and they will give the entire presentation. Please show the email ID once. So it is msranade@gmail.com. I can MS Ranade, RANADE, only RANADE, msranade@gmail.com. It is fairly simple email ID. How rows of the coil is cooling coil? There is a software available, and it is very complicated heat and mass transfer process, and it can be done only by, mostly done by software. In a fit out job, we have to select the room air quantity based on select AHU, ADP or calculate. So to find out the dehumidified air in the applied psychometry, there is a clear-cut process. It is a case of applied psychometry and not the part of basic psychrometry. Where on the y-axis you said it is only humidity ratio, and where we can find value of absolute humidity. In the psychrometric chart, there is no absolute humidity is denoted. It is only humidity ratio. Because you have mentioned delay in equilibrium status of heat in the wet bulb trunk thermometer, I have not understood the question. Regarding the puzzle, fog is nothing but water. I think I am not going to answer the puzzle. You have to send me by email. Can we directly plot on psychrometric chart increase in RH with increasing the airflow? Again, it is a question of psychrometry, applied psychrometrics. In a split AC, we have fog issue. How can I address this issue? Okay. If you have a fog issue, I don't know exactly, but you may try to put a screen jali, very jali, and try to remove the fog, or you can put a heater after that. Where we can find a derivation. If you write to me, I will send you the derivation from the book. msranade@gmail.com. Is there any methodology to IADP? Indicated ADP. Of course, there is a methodology to calculate indicated ADP, and that is given in the carrier handbook or any applied psychometric book. I think there are so many questions, but I think there is a limit to answer. Email ID of Ranade sir. Again, I am giving msranade@gmail.com. Okay, I think those are the question and answers. And Saloni, I think with that we can perhaps end the session.